I'm going to talk about the second derivative test for maxima and minima, etc. in two variables, and going to show some examples. I'm not going to prove anything super carefully, but I'm hopefully going to give enough examples to convince you that the test I'm going to propose makes sense. This is the standard test that's in any multivariable calculus book. So I'm going to look at the graph of a function z equals f of x, y. So for example, maybe z equals x squared plus y squared. That's a nice parabolic bowl. It's a circular paraboloid, in other words. Very straightforward. We know what that looks like. And I want to think about critical points. Well, first of all, a critical point is pretty easy. Critical point is just something where the tangent plane is horizontal, just analogous to one variable calculus where the tangent line is horizontal. And so you're just going to set fx and fy to be 0 and figure out what points satisfy that. A lot of the work of max-min problems is actually doing that algebra, but that's not what I'm focusing on here. Okay, so at a particular point, suppose we found a critical point, what kind of behavior do we have? Is it a local maximum? Or another word for that is a relative maximum. I usually say the word local. Um, is it a relative or a local minimum? Is it a saddle point? That's the kind of thing you can't have in one variable, but is a cool new feature. Or is it something else? Is it something weirder? Is it something that doesn't fall into these three classifications? Most nice functions, most critical points of most nice functions fall into these three categories, and we're going to focus on those, but there's might be something weird going on. Okay, so in analogy to one variable calculus and just thinking about what's different between these max, min, and saddle, it's about how they're curving. Maxima should curve downward in all directions, minima should curve upward, saddles should curve differently in different directions, and that concavity or curvature is going to have to do with second derivative. So here's a hint, a big hint. We're going to create a matrix. There's 4 second derivatives that we could take in principle at a point. The xx, the xy, the yx, and the yy. And I'm going to suggest putting those into a matrix. Now, fxy and fyx are all exactly the same number by Clairaut's theorem. We're never going to try to do this where Clairaut's theorem is violated. You could, and it's some of these funky, subtle examples, but we're not going to try and do that. So this is a symmetric matrix. In other words, it's equal to its transpose. For a 2 by 2, that just means that the two off-diagonal elements are equal. But it's still actually, even though it seems maybe redundant, it's still good to put this together as a matrix. Okay. Now, really, what we should say is, okay, at a specific point x naught, y naught, we create this matrix of fxx at that point, fxy at that point, etc. So it's going to be this matrix of numbers. Now, you can go ahead and put together, do it as a function, this function of x and y, 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 and then just evaluate it at points. But in the end, we're going to be interested in the numerical values at these specific points, at the critical points. This is called the Hessian matrix. And something else is going to be called a Hessian sometimes as well, which we'll get to. But this is the Hessian matrix. That's just a guy named Hess said, hey, let's put the second derivatives in a matrix. Okay, so let's look at examples. That's what I really want to focus on. If f of xy is x squared plus y squared, that's the example. I'll flash that up in a second. Then the Hessian matrix is just 2, 0, 0, 2. The cross derivatives vanish pretty easily. You might want to pause and calculate the second derivatives for yourself. I'm not going to do that. So, and that's a case where we've seen that it's clearly a local min. Okay, not too shocking. X squared, the traces are x squared in one direction and y squared in the other. And of course, those are going upward. So there's really no shock or surprise there. Okay, next example. Now, we're trying to have enough examples to figure out, suppose you only gave me those 4 numbers, or this matrix, there's really 3 different numbers, how could I figure out what to predict without going to the graph? So this is just one piece of evidence so far. Okay, next, f of xy is minus x squared minus y squared. Well, okay, that's this function, graph that, surprise, surprise. It's a downward facing bowl. That's a local maximum. And of course, it's not too surprising that along the x direction and along the y direction, we're getting downward parabolic behavior. And it's not completely obvious, but in all directions, in fact, we're getting downward parabolic behavior. Okay, so what we've got there, of course, is that the Hessian has just minus 2, 0, and 0. Again, you might want to pause and check the second derivatives. Although if you believe this first one, I think you're going to believe the second one. Now let's get to something more interesting. Let's purposely do a saddle. Well, z equals x squared minus y squared, or f of xy is x squared minus y squared. That is the simplest way to get a saddle. Not too hard to see that, again, the mixed partials are 0, and the second derivatives now, I should have said, because these are quadratic functions, the Hessian, even as a function of x and y, they are constant. But what I really am interested in is at the origin, which is, it's easy to see that those are the critical points of these guys. I get these numbers as well. Okay, so really I'm picking a bunch of examples, I should have said that, with critical points that happen to be at the origin, just for simplicity. Nothing really special about that, just for simplicity. So here, the second derivatives are positive 2 in the x-axis and minus 2 in the y-y. So what's happening here is that this is registering, like in BC Calc, this would be a min when I look in the x direction, fxx. That's a section, that's a concavity of a section along the x direction. And it's trying to be a max, curving downward, concave down, in the y direction. So surprise, surprise, it ends up being a saddle. So let's click on the saddle function here, graph. Ta-da, okay, it's a saddle. Oh, that really is sensitive, okay. And it indeed curves down in y and up in x. So that's, again, not a big surprise, although that is something that's really different that happens in multiple dimensions that you can't have in one dimension. Okay, I don't want to make this particular video too long, but I want to get to a little bit of the punchline. Let's look at 2xy. That we have seen before. A lot of people might have seen that before. Let me actually just replace 2 times x times y. And oh, look, it's a saddle again. Now it's a saddle where the up directions are where x equals y. It's not too shocking. If x equals y, you're going to get 2x squared. And the down directions are where x equals minus y. If x equals minus y, this is just minus 2x squared. So again, you get parabolic behavior in one direction, and in the perpendicular direction, you get parabolic behavior, but going downward instead of upward. Again, a saddle. Okay. A cute way to see that as well is in polar. X squared minus y squared is r cosine theta, quantity squared, minus r sine theta, quantity squared. So a factor of r squared, and then cosine squared minus sine squared is r squared cosine 2 theta. This one is 2 times r cosine theta times r sine theta. So that is just r squared and then 2 cosine sine. Oh, that's just sine of 2 theta. Very, very similar, just using sine instead of cosine. So they just rotate in terms of which thetas give you positive, which ones give you 0, which ones give you negative. Okay, so these are extremely closely related functions. They're really the same graph, just rotated. But the HF, the Hessian, looks quite different. This is the first one where we've seen some mixed partials showing up. And the unmixed partials are 0. So somehow the second derivative test has got to say, take this matrix and say minimum, this matrix and say maximum, this matrix and say saddle, and this matrix and say saddle. And in the next video, we'll see what that test would be.